Hello students, welcome to another session of All Force e-learning program. We shall take up the applications of the electric potential due to a point charge. We will talk about the various applications due to a point charge, the electric potential due to a point charge. So before going to this, let's have a recall of all the things what you have learned. So charge, fundamental quantity. Every charge has a field space around the charge where you can experience the presence of it is electric field. The measure of number of lines of force, electric field produces lines of force, right? So the measure of number of lines of force passing through a space is electric flux, right? Flux. The number of lines of force per unit area is electric flux density or electric field strength. Then according to Gauss law, charge per unit, the flux passing through an enclosed Gaussian surface is charged by epsilon naught, Q by epsilon naught. Then electric field intensity is the force experienced per unit charge, and we have derived the formula for the various electric field due to different charge distribution. Then we have talked about potential. Potential is the electrical state of the body which determines the direction of flow of charge, whether the charge is going away from it or charge is coming into it, right? So potential is state. So you can even define it analytically. The definition for electric potential is, so the potential V is the amount of work done in moving a unit positive test charge from infinity to the point in the field. The amount of work done in moving a unit positive test charge from infinity to the point in the field. So V is W by Q naught, electric potential. So it is the amount of work done per charge Q naught, like this. Well, cross multiplying, I get W as V Q naught. This is the work done. Then electric potential units, volts, joule per coulomb or volts. Dimensional formula Mn square T minus 3 I minus 1. It's a scalar. Even though it is a scalar, it can be positive, negative and 0 also. When positive, negative I have defined. Now according to our this thing, now coming to the actual topic. Suppose if I consider a point charge Q at a distance d, then the potential at this point V is given as 1 by 4 pi epsilon naught Q by d. Now this is the formula for the potential. So potential due to a point charge. A point charge fixed at point O, then the potential at point P, 1 by 4 pi epsilon capital Q by d. Right? Now this is a scalar. For a positive charge, if I consider a positive charge, if Q is positive charge, then the potential is 1 by 4 pi epsilon naught plus Q by d. If Q is negative charge, then the potential is 1 by 4 pi epsilon naught minus Q by d. It's minus capital Q by d. This is the potential, right? So potential of the point, potential due to point charge at infinity, at infinite distance is 0. We cannot define the potential due to a point charge at its location. At its location there, you cannot define the potential due to point charge. Okay, so these are the formulas. Okay, now looking at the potential of the charge, potential of the point charge, this is the formula for the potential of the point charge in a when it is placed in air vacuum free space. Suppose if the same charge is placed in a medium, in a dielectric medium, there is a dielectric medium K. If it is in this medium and you are asked to find the potential at a point, then I have explained in a dielectric medium, the electrical permittivity is epsilon, which is K times epsilon naught, where K is called dielectric constant. It is epsilon by epsilon naught, or relative electrical permittivity it is, right? In air, when you are in air, the electrical permittivity is the absolute electrical permittivity of free space, epsilon naught. You know the value, epsilon naught is equal to 8.854 into 10 power minus 12 coulomb square per Newton meter square. This is the absolute value in free space. But suppose if you are in a medium, when the charge is in a medium, then it is K times epsilon naught, where K is called dielectric constant, specific inductive capacity or relative permittivity, electrical permittivity. So cross multiplying this, epsilon you can write as epsilon or epsilon naught, or it's k epsilon naught. So therefore, now, so in a medium the electric potential is 1 by 4 pi. If it is in medium, it is epsilon capital Q, the charge Q by distance r, or d, whatever it is. So when it is in a medium, then it is 1 by 4 pi, permittivity of the medium, into Q by FD. Well, V is equal to 1 by 4 pi. Epsilon you can write as epsilon or k epsilon naught into k, capital Q by d. So now the potential, well, this is the potential of the charge when it is in air. This is in medium, it is in medium. So potential in medium is potential in air by k. So whenever the charge is in medium, then the potential decreases by k times. It reduces by k times. So the effect of the medium on the potential varies inversely with k. So that is V1 by V2 is K2 by K1, or V1 K1 is equal to V2 K2. The effect of the medium on the potential, whenever the charge is in a medium, direct medium, potential reduces k times. So therefore V1 K1 is V2 K2. Right? Similarly, the potential due to a charge is directly proportional to charge, the amount of charge. V proportional to capital Q. So V1 by V2 I can write as Q1 by Q2. And of course, potential inversely proportional to distance. V inversely proportional to the distance of the point R. So from this, I can write V1 by V2 is equal to R2 by R1, or V1 R1 is equal to V2 R2. The comparison of the potential, it is inverse. As the distance increases, potential decreases. The effect of this charge on the point, as the distance, the effect decreases. Right? So therefore the effect of the point, charge at that point reduces. So therefore the potential also decreases. As you move away from the charge, potential varies. Potential is decreasing as you move away from the point charge. So the potential is inversely proportional to distance. Putting all the things into one slot, this thing. So it is Q1 by Q2 directly proportional to charge, inversely proportional to distance R2 by R1, and inversely proportional to the dielectric constant K. So comparing the potential for two different entities, for two different charges, for two different points in two different media, then V1 by Vt is Q1 by Q2, R2 by R1, K1 by K2. Right? So this way you can compare the potential due to a charge at various points like this. Right? So let us take a very simple problem based on this. Consider a charge, let's say a 1 coulomb unit charge, 1 coulomb charge. The potential due to unit charge at unit distance is 1 meter. Right? A simple standard question. The electric potential due to a unit charge at unit distance is measured as, well, due to a point charge, we know the formula is 1 by 4 pi epsilon naught Q by d. Substituting the values, it is 9 into 10 to the power of 9. You know 1 by 4 pi epsilon naught value is 9 into 10 power 9, because I have given you epsilon naught value. It is either 8.854 into 10 power minus 12, or you can write it as 1 by 36 pi into 10 power 9. You can even denote this way. So now putting this in 1 by 4 pi epsilon naught, it is 1 by 4 pi into epsilon naught. It is 1 by 36 pi into 10 power 9. So pi gets cancelled. This is 9 and this goes up. So therefore you get the constant, Coulomb's constant in air vacuum free space. It's 9 into 10 power 9. Now the charge given is 1 coulomb unit charge. Distance of the point is also 1. So therefore the potential V is equal to 9 into 10 power 9 volts. You know, this is a very high voltage, very high value of the potential there. A unit charge at unit distance produces very high value of potential. Well, for our calculation, it is 9 into 10 power 9 volts there. Okay. One. Now let us calculate the electric potential due to a point charge. Let's suppose there is a point charge Q at a point O. Imagine a circle around this point charge. A circle around this point charge at a distance r. Now potential due to this point charge at various points in the circle. So when the charge is here, now this is at point at a distance r. So the potential here, let the point be A. Potential at A is 1 by 4 pi epsilon naught. Its capital Q by the distance is r. Consider another point here, point B. Even this is also same distance, same charge, same distance. Here also the potential is same. So this is VB. Here at this point C, same distance, the potential is same. And even here also the potential is same. Right? So at all the points on the charge, the potential due to point charge is same. At all the points on the circle, at all the points on the circle, the potential due to this point charge is constant. So now this, the locus of all these points, when I combine this surface, that you can term it as equipotential surface. The locus of all the points where the potential due to this charge is a constant. So the potential due to this is a constant at all the points. Now combining all those points, the potential is same. An equipotential surface like this. Similarly, let us take up, suppose if a charge is placed at, let us consider an equilateral triangle. A charge is placed at one of the corner. Now you are asked to find the potential at the other corners. Let this be A, this be B, and this be C. Now he is asking to find what is the potential difference between A and B. Potential at A and potential at B, right? So potential at two different points. This is an equilateral triangle of side A, suppose. Equilateral triangle of side A. Then potential due to this. Now this is a point charge, distance of the point is A. So potential at A is equal to 1 by 4 pi epsilon naught. The charge is Q and the distance of the point is A. Similarly, the potential at B is 1 by 4 pi epsilon naught. The charge is Q. Now this is an equilateral triangle. The side is same A. So it is capital Q by A. An equilateral triangle, all the three have the same side. So therefore the side is A. So therefore when the charge is at one of the vertex, then the other two vertices, at this other two vertices, the potential is same. So potential at A is equal to potential at B. Suppose if he is asking you to find the potential at the centroid. At the centroid O. Right? So what would be the potential at the centroid O? You know, in an equilateral triangle of side A, if I drop a perpendicular like this, the altitude, the length of the altitude, right, and this point will be the median. It cuts the median in the ratio 2:1. So by that, the distance of the point from the vertex to the center is A by root 3. So therefore the potential is 1 by 4 pi epsilon naught. The charge is Q by distance of the point from the charge. It's A by root 3. A by root 3, and this root 3 comes up, it is root 3 times here. So potential at the center O is root 3 times, it's root 3 times 1 by 4 pi epsilon naught Q by A. Well, potential at any vertex is Q by A. So potential at the center O is root 3 times the potential at any vertex A or B. Similarly, suppose if he is asking you to find the potential at D, which is the midpoint here, right? If I drop a perpendicular, this is the altitude, length of the altitude in a equilateral triangle, right? Suppose let this distance be D, we don't know. This angle is 60 degrees. This is a perpendicular. When I draw in an equilateral triangle, the altitude is the median or perpendicular bisector, all the three are same. So considering this right angle triangle, take this right angle triangle. If I consider this right angle triangle, then sin theta is opposite by hypotenuse. Sine 60 is opposite d by a. But you know the value of sine 60 is root 3 by 2. So cross multiplying d is root 3a by 2. So the length of the altitude is root 3a by 2. So the potential at point B, it's 1 by 4 pi epsilon naught capital Q by distance of the point D, that is root 3a by 2. 2 goes up. So potential at D is 1 by 4 pi epsilon naught 2q by root 3a. This is the formula. So this way, potential due to a point charge at various points. First we have considered a circle, later we have taken a equilateral triangle. Suppose now if I imagine a square, suppose he has given, right, he has given a square like this, square. Now a charge is placed at one of the vertex. He is asking you to find the potential at the other vertices. You know, in an equilateral triangle we got the potential at other vertices are same, but here let this be A, this be B and this be C. Well, square all sides are equal. Now potential at A, charge is plus Q, distance is A, so potential at A 1 by 4 pi epsilon naught Q by distance A. Right? Similarly, potential at C, this is point C, VC 1 by 4 pi epsilon naught, charge is Q, A, it's Q by A. So potential at A and C both are equal. How about B? You know, B is diagonal away from point this point. Let's suppose this point is D. So it is diagonal away. So this is A, this is A. So the length of the diagonal square we know it is root 2A according to Pythagoras theorem. So the potential at B, VB is 1 by 4 pi epsilon naught charge Q by the diagonal it is root 2A. So potential at B is this 1 by 4 epsilon Q by A, I can replace it as potential at C, it's VC by root 2. Now suppose if he is comparing, writing the inequality, the potential at A is VA, potential at B is VB and potential at C is VC, then he is asking you to compare the potential. You know, A and C both are equal. So potential at A equal to potential at C. Then how about B? It is VC by root 2. Right? 1 by root 2. You know, 1 by root 2 value is nearly 0.7, approximately 0.7. So therefore it is 0.7 less. So the potential at point B is less than VC. So potential at C is greater than VB. You see the distance is more. B is at more distance than compared to A, and A is at A, B is at C is at A distance, but B is at root 2A. When distance increases, potential decreases. So potential at B is less, A and C are more. He may ask you to compare the potentials like this. Okay? Well, now coming to potential difference. Now, suppose there is a charge positive plus Q. There are 2 points A and B which are at a distance small a and small b from this point charge O. Now he is asking to find the potential difference between A and B. Well, you know, from this point charge A is at a distance A, so small a. So the potential at capital A is 1 by 4 pi epsilon naught capital Q by A it is. Now similarly the potential at point B, V, it is 1 by 4 pi epsilon naught capital Q by B. Potential at B. Now the potential difference between A and B, delta V. So it is potential at A minus potential at B. Potential difference between A and B, potential at A minus potential at A minus potential at B. It's 1 by 4 pi epsilon naught. It is 1 by 4 pi epsilon naught capital Q by A, potential at A, minus 1 by 4 pi epsilon naught capital Q by B. So 1 by 4 pi epsilon naught, if I take common, even Q also common, then it is 1 by A minus 1 by B. Or simplifying, it's Q by 4 pi epsilon naught, denominator AB, numerator B minus A. So this way the potential difference between these 2 points. For a point charge on a line, on the same line, if I am comparing the potential difference at 2 points, then the potential difference at 2 points is Q by 4 pi epsilon naught B minus A by AB it is. Right? So next, potential difference for a point charge can even be expressed like this. Suppose potential, there is a point charge at point O. There are 2 points, A and B. Let us say capital A, which is at a distance small a, and another B at a distance small b, like this. Now question is going to ask you like this. Now what is the work done in moving any other charge? Work done in moving in another charge, let us say small q. What is the work done in moving a charge small q from B to A? The question, work done in moving a charge small q from B to A. Right? Now, according to the definition of potential difference, delta V is equal to W by Q. Right? So, therefore, work done W is equal to cross multiplying potential difference into Q. So, the work done in moving a charge small q through a potential difference delta V is delta V into Q. So, therefore, substituting work done is potential difference V into small q. Well, we have just now found the potential difference between these two as 1 by 4 pi epsilon naught, capital Q common, it is 1 by A minus 1 by B. Right? This is the potential difference into small q. So, therefore, the total work done in moving the charge 1 by 4 pi epsilon naught, the LCM is AB and it is B minus C. A very beautiful question. Work done to move the charge from the farther point B to the initial point A. So, W is 1 by capital Q small q 4 plus naught B minus A by AB. Work done. Instead of asking the potential, he is asking you to find the work done there. Same thing. Let us put this in some more key terms there. Right? Now, suppose, imagine there is a setup where the electron is accelerated, or the electron is moving from high potential to low potential, or I have to move the electron from low potential to high potential, then work done. So, in a region, suppose there is, let's suppose the potential here is VA, here the potential is VB. So, between these two, the potential difference is VA minus VB. Now, what is the work done in moving a charge from lower potential point to higher potential point? We know work done is potential difference into charge. Suppose if I am moving an electron, then the work done is potential difference VA minus VB into, it is minus E. The charge of electron is minus E. So, work done on the electron in moving through a potential difference, it is VA minus VB into, this is minus E. So, work done on the electron is minus, if I multiply, I get VB minus VA into E. Imagine, suppose there is a setup where the potential, it is high potential, this is low potential, high is represented as plus, low as minus there. Then if the electron, if the electron is moved from minus to plus, electron, you need not do work. Electron is attracted by the positive charge. Electron is repelled by the negative charge. So, electron accelerates like this. Electron will accelerate from here to here. So, with respect to the electron, here the potential is more, here the potential is less. So, from high potential to low potential, it gets accelerated. Therefore, the energy gained or work the energy gained by the electron or work done by the system, by the setup, then the energy gained by the electron you can write as potential difference into the charge. Right? Energy. So, potential difference into charge. So, when the electron is moving from here to here, it is losing its potential. For an electron, here the potential is high because electron is minus and this is minus. Minus of minus is plus, here the potential is high. Electron minus, this is plus. Plus into minus is minus, here the potential is less. So, when the electron moves from here to here, it is moving from high potential to low potential. It is losing potential energy. Loss in potential energy of the electron. Loss in potential energy of the electron is the potential difference between these two, delta V into E, and this loss in potential is equal to gain in kinetic energy of electron. It's gain in kinetic energy of the electron. So loss in potential energy or gain in kinetic energy is potential difference into E. This is the formula, right? So therefore, well, potential is VA is into E, magnitude wise, right? Magnitude. I have already stated that it is a gain. So it's VA minus VB into E, or loss in potential energy, VA minus VB into E. Actually it is VB minus VA into E is the work done, but loss, I have stated already, the energy is lost, so it is VA minus VB into E. So that is equal to the gain in kinetic energy. So based on this, I shall now derive a very important formula which will be helpful for you in future study there. Let's suppose there is a uniform electric field between the capacitor plates. The potential difference between these two is V. The potential difference itself is V. Potential difference between the plates itself is V. Right? Now the charge Q is accelerated from here to there. A charge Q, let's say plus Q. When plus Q is here, then for positive charge here the potential is high. When it comes here, the potential is less. So the charge is accelerated from here to here. So it is repelled by positive charge, it is attracted by negative charge. So this positive charge is moving from high potential region to low potential region. So it is losing potential energy. So the loss in potential energy is potential difference into charge. Well, it is given that the potential difference itself is V. The potential difference is V. So the loss in potential energy is VQ. And this loss in potential energy, due to this loss in energy, the charge is accelerated. An accelerated charge gains velocity. So the gain in kinetic energy is half mv square. According to law of conservation of energy, energy can neither be created nor destroyed. So the loss in potential energy is gain in kinetic energy. So therefore loss in potential energy is gain in kinetic energy. So loss in potential energy VQ is gain in kinetic energy half mv square. So therefore the velocity gained by the charge. The velocity, this is velocity. When it has reached the other end, the velocity is small v. So the velocity gained, cross multiply. So it's 2 capital VQ by M is V square. Or the velocity gained V is under root 2 VE by M. A very beautiful formula. Whenever a charge, VQ, we have taken it as charge Q. Whenever a charge Q is accelerated through a potential difference V, in a sense, the charge is going from high potential to low potential. It is losing potential energy. So when it loses potential energy, it gains kinetic energy. So when it is gaining kinetic energy, in the sense velocity is increasing. Then the velocity gain, starting from rest here. So the velocity gained is under root of 2 VQ by M. A very important formula which will be helpful. Suppose had the charge been electron, if it is electron, so the velocity gained is under root of 2v, the charge of electron E by M. I am writing the magnitude only, mass of the electron. So the magnitude of the velocity of the electron is under root of 2. V is the potential difference through which it is accelerated. E by M value, this is the specific charge of the electron. The specific charge, right? So it is it's E by M. So substituting this value, you can simply evaluate the thing there. You know, this is 1.71 into 10 power 8 or 10 power 8 CGS units, 10 power 11 SI units. So into 2. So this approximately comes up to be, this is approximately 6 into 10 power 6 root V. You know, this is an absolute value. In calculation, you can use this formula. I am putting it I have already substituted the value of charge of electron 1.6 into 10 power minus 19, 9.1. You know, mass of the electron 9.1 into 10 power minus 31. Then this value comes out to be 1.78 into 10 to the power of 11. Well, 2 into 1.78, approximately 3.5. Okay, 3.6. So let me take it as 3.6 or 36 into 10 power 10. Sorry, it is 5. 36 into 10 power 10. So under root, it is 6 into 10 power 5 root V is the potential difference. Simply make a note, it is 6 into 10 power 5 under root. Very absolute value. Good, right? Thank you.